I'm Peter. I'm the session chair of the session. There's too many sessions in that. I'm here. So today we're going to be having a quick talk by Navid. He's going to be talking to us about architecture, real-world, physical, actual architecture, as opposed to the wonderful airy-fairy stuff we normally deal with. And he's going to talk about how to use Python and data to improve the architecture that we get. Sounds really cool. Looking forward to it.
One. There we go.
What was the problem?
Don't know. Turned it off and on and it worked.
Okay, so I do the same. Can you hear me now? Cool. Wow, lots of people are here. I'm wondering why you're here now. Because there are very fantastic speaks on other rooms. So, you might be interested in architecture and know some new fields and to see what we do in architecture. And so, let me start. First, I need to introduce you the interface that we use to coding. Actually, I had some slides to show you, but why not going through the program? We use Rhinoceros. It's a very popular software that architects use it for doing some 3D modeling. And inside the Rhinoceros, we have Grasshopper as a plugin. Actually, the Grasshopper gives us an opportunity to do some algorithmic program inside the Rhino. And where is Python now? The Python is in the, we have a component which is actually Python. Now we have Python inside the Grasshopper and the Grasshopper inside the Rhino. So we can start coding here. But I'm not going to do that in front of you, professionals. So we do coding inside the component, and then we just need to close it. We use this part as an input data, and after solving by the code, it gives us the output. Then we can add more input and get lots of output. Then we're going to have a series of components to solve our problem or gives us our algorithm. To give you some example, so this Rhino, Grasshopper, components, and then Python. And we code inside the Python. We need to have these three software inside each other to be able to coding in Python and using the Rhinoceros as an interface of our model. One of the examples that I showing you guys here first is to give you a concept of adding data on geometry and how we do that. It's a very, very basic example that I'm trying to show the concept. Imagine a grid of points, and we had a criteria to make this grid. What's the criteria? The criteria to organize these points are, for example, same x and y, same direction of x and y. What if we add more criteria on the grid of point as a very basic example? And by having two more points, two, for example, polar point or attractive points, then we can add more criteria to draw some circles on each point of grids, of each point of grid, and determine the radius of each circle based on the distance from those 2 points. So we end up with new patterns, and we can organize or design based on different criteria. What if we move the points based on these 2 points, based on their distance? What if we move them? It would be another criteria. What if we move the points in Z direction, in Z direction? Then you're going to have a different geometry. And then, instead of having 2 main points, what if we have 4 points? Then we're going to have a new shape with the same algorithm. Oops. And by a very simple code, we can make it more and more complicated. What if we add a structural criteria to make some geometry like this in architecture? It's the same idea. We started with the grid of points, and now we have a proper structural geometry that we can use in architecture. This is another example. I haven't done this. I'm using this as an example. Imagine a very simple brick wall. What if we add data on each brick? This is a very simple example that shows us the effect of adding data on each brick by rotating each in different orientation, and get the nice pattern out of it. This is another example. It's the same as the grid of points, but it's a grid of boxes, and each box is rotated based on the designer desire, and it gets the different patterns. I used the same concept to design this facade. The challenge was to not getting the west direct sunlight. So we add data on different windows to be oriented in north and south, to not getting the west direct sunlight, as an example. I hope you get the concept of adding data on the geometry. But what we do these days in PJ Crow Consulting, as an engineer consultant, we help architects to improve their buildings and in terms of energy consumption, and make people more happy and comfortable in interior spaces and outdoor spaces. This is the 360-degree photography from the Manhattan train station. It is designed by Santiago Calatrava. And one of the new challenges in architecture is to analyze the visual discomfort through the year. And so now we have a big issue with openings and facades, and we have lots of problems for people and users in the building, which they have a visual discomfort and makes problem. And how we can solve the problem: first we need to analyze the building. For example, we know the sun position through the year. Can I go and... We know the sun position of the... We know the sun position from to the annual sun position, and we can overlay these data on the image or photograph on an actual building, and to see which part and from which date we have a problem. So it's easy to analyze this kind of problems in an actual building. We also had the same problem in a building which is designed in Johannesburg, and we had a problem. We had the challenge of solving this issue, a discomfort glare issue, which comes from the skylights. So we made a Python code. We made a Python code to analyze each skylight, and the Python code is able to give the skylight depth and see the most effective part of the skylight. It is also, the code is able to determine the opening area. It's also possible to move the opening area in different direction. And then if we add all of this possibility together, we're going to have this kind of shape, and we can see the effect of each opening on different area of the building to see the effect of the skylight on each building, where we have problem and where we don't have problems. And by changing the geometry, we're going to have less and less glare problem issue. And also at the same time, we can see from when we have this problem. If it repeats every hour of the year, then it's a problem. If it happens once a day, so it might not be a problem. So the sequence of the problem is also important for us. And by changing the geometry, the program understands the effect on the building. And then, as an example, and then we need to record the process. We can't just get the result and write the code, get the result. It's not acceptable. We need to see how it works. And so we record the process. And for example, in this case, this is just one cell from the skylight, which we had almost 3,300 hours glare problem. And by optimizing, it doesn't play. By optimizing the geometry, we are getting less problem, and the program is optimizing the glare issue with the minimum fabric usage. So we had different criteria for this optimization. Another solution for that skylight is also, we can add more surfaces on behind of the skylight before the direct sunlight comes through. So we bubbled up each skylight to see the most effective part of each in terms of glare issue. Then the code gives us a better understanding of the most problematic part of each skylight. Then we can add more surfaces Then we suggested these surfaces to the architect to solve the problem issue in a very in an early stage. Another example is to using the kinetic cells. These cells can be open and closed and something between to manage the direct sunlight through the whole atrium. So we don't care about having direct sunlight in the ground floor. People, they like it. But we do have problem if we have glare on desks, especially in library, offices, etc. So we try to manage this kinetic cell. We try to program these cells to be open and closed during the day in terms of having no glare on desks. You might see some glare issue here, but you're not going to see any problem issue on desks. And we don't care to have a glare issue on the ground floor. Another example, am I going so fast? Lots of time. Another example, I'm getting slowly. Another example of optimizing the daylight in urban design is to getting the best, the challenge is which orientation gives us the best daylight and how we can optimize that. So we made this little blue box and we made a program, and to be the intelligent creature, and then we ask the box, go and find the best solution, go and find the best optimum solution to catch the best daylight. And then it ran away. Where are you going? Our land is here. So it was so funny for us that the creature was so intelligent that he knew that there is no way to catch the best skylight in the middle of the context. So he ran away and expanded to get a better result. Then we said, okay, please stay here. We made this limitation. We need to solve the problem here. Don't run away. And then it becomes taller and taller based on our limitation, and expand like this in the middle of context to get the better daylight. Another example of analyzing the environment in architecture is, and we are busy with these days, is analyzing the outdoor thermal comfort. We are trying to encourage people to be in outdoor spaces and enjoy the outdoor spaces. In terms of, we can save lots of energy, we can make people socialize, and we can, there are lots of benefit out of it. Recently, we presented our methodology in a conference in Los Angeles, and we got the Best Paper Research Award. And we do a lot for, we've done a lot for getting this methodology. There are lots of different calculations, and for example, running the CFD is just the small part of it. And then doing some solar radiation and surface temperature radiation. We need to overlay all of this data to analyze a point in an urban area to see how comfortable is that for a person in the outdoor. Basically, it's the same concept of backward ray tracing. If you are familiar with the backward ray tracing or backward path tracing, it's the same concept. We distribute lots of points on a sphere to project the environment in a sphere as a human body. So by having lots of points, we're going to have lots of vectors, lots of rays to shoot. And if it hits each surface, then we're going to have the information on a sphere. By increasing the density, we're going to have better results. More and more, better results. Then we can project each surface on a sphere, and it's possible to do it for a very complicated geometries. Yeah, we do math. We made new formula to solve some challenges that we have in the form and the main equation, and this is new. So, and we've done all of this process, and we gather all of this information and overlay all of them through the one process, one loop, which in the past we had to do it with different software. Lots of they were very time consuming, and we couldn't handle that because it wasn't possible to overlay different data from different software, and it doesn't make sense to analyze the 1 hour of the year, and it takes 4 hours in a real time. So we made this very fast, quick process by several Python coding and overlaying all of the information at the end, and to see how comfortable is each point. We also optimized the mesh, which point we need to examine. The points which are more close to the geometry, we are more interested to know the result than the points are further. So we can analyze the outdoor comfort in different points and visualize that even for a very complicated geometry. To understand the results, then we had to use different data visualization. The parallel multidimensional diagram helps us to understand the result. And by changing the domain, we can see and we can compare and see what was the problem that makes heat stress for a person in that point. And for example, for a point 19 that I showed in the previous slides, we had lots of heat stress even in a very low sun direction. And what was the problem? We can find a way of the problem by, for example, having a very high surface temperature radiation, which we can then affect the surface materiality. So this is the annual result for each point. Then we had, for example, 1,000 points. This is just the visualization of the annual result for each point. Then another solution that we made a Python coding for it is to find the most effective parameters that affect the outdoor comfort and made people discomfort. In this case, we choose the one path with different parameters value that makes heat stress. And we had to look for a very similar situation which makes people comfortable. To finding the closest situation, it's a very complicated math coding, and we use it to find the similar situation, but the different result. And it gives us the answer. The most effective parameters are the low wind velocity and sun direction on that point. So if we try, and it gives us some design solution. And this is and then we can improve the situation. We can improve the annual outdoor comfort. For example, in this case, we improved the design by 50% comfortable and 50% not comfortable, which we couldn't do anything for midnight, because it has different time period. So this picture is just a visualization. We need to talk to architects, which they don't know how we gather data. Then we found this kind of visualization to show them which part of the urban area is more important for a person standing there, and showing some radiation comes from the shortwave radiation comes from the sun, and the diffuse radiation comes from the sky, and surface temperatures, and which points are more important for that person, which are mostly here, and if we go further, less points are important for the person. And then density is important, and the reflection is important. The reflection of the sun shortwave radiation, which goes through the surface and it goes to the person and makes this person hot and feels heat stress. So this is another example. We go through it was green now, you couldn't see that. It gets heat stress because the environmental issue, actually the most important was the sun direction, and now it feels better because in the shadow, and in some case it's in between. And these bar charts show the surface radiation, and it shows the direct sun radiation. Then we can have a better idea about our environment. That's it. Thank you.
Oh, that was pretty freaking awesome. Does anyone have any questions?
On the first building that you showed, it looked like the skylights were in kind of a Voronoi pattern.
Yeah.
Was that an already built building that they had problems with, or was it something that they were doing as part of the design?
Actually, we suggested that pattern.
Mm-hmm.
And you want to know why? It was because if we suggested a very specific grid, then it's not flexible for us to make it smaller and bigger. But in the Voronoi shape, we are able to make them smaller and bigger and change the pattern based on what we want. Now, because that cells, they shouldn't be similar size in everywhere. In some case, which the program tell us it should be 3 meter depth, we can't make it. We need to make it smaller and have 1 meter depth.
Okay, so you actually optimized the shape of the Voronoi pattern as well.
Yeah, we had. I don't have a slide for it, but first we analyzed the whole atrium based on the grid to see from which part of the atrium we need, for example, a grid of 1 meter by 1 meter, and it gives us the depth. It should be 4 meter depth. If it's 1 meter by 1 meter. Then we had a pattern to expand this Voronoi shape on it. Thank you.
How do you accurately?
Sorry.
How do you accurately record the sun position? Because you have a 360 you have X number of days in the year,
Mhm.
and where is it relative to?
The sun path diagram which we use is a very common it's a very common diagram that we use in architecture, and it shows the different sun position through the year based on the latitude and altitude of the geographical data on each city. Yeah.
Do you find that the architecture sector is very open to this kind of approach, using programming and data in the architecture, or is this more of a new thing that's happening now?
Actually, what I showed you, it's not actually a very new things. Our methodology is overlaying data, and our method is new. But using digital architecture, you can Google it, parametric digital architecture, and so on. It gives you an idea about how the usage of programming in the architecture. Yes, we do appreciate that because we show them how to improve their design. We don't give them a new design. I think this is the key, that we need to help them. And when they see this approach, they accept it.
How do you balance the aesthetic problem and the optimization problem? For example, with the Skylight, adding the additional surfaces, it was quite an organic, quite a beautiful result which came out. And yeah, how is that negotiated between the architects and the engineers? So versus making it pretty versus making it functional.
Both, actually. We can't make an ugly shape and say, this is the best solution. It doesn't work like that.
That comes from you as well. That's part of your task there, is to actually conform to this.
Yeah.
Okay, cool.
And unfortunately, we have to make pretty renders, and to make it pretty is always part of our job to do, Convince the architect to have this kind of things. Did I answer your question?
Yeah.
Okay.
That building in London that melted people's car dashboards and whatnot a few years ago. So that firm obviously didn't do anything like this, so it's not common?
Actually, the report that you got from that building was they didn't wait for the building to be finished. Now there are lots of louvers in front of that building. It doesn't make any problem. And but they can do the same process as we did for the environmental analysis.
Hi. So I'm not sure if the examples that you showed us were for buildings that had been designed already or in the process of being designed or maybe even built. But how does this kind of methodology compare with just actually measuring stuff? Like, it feels like in a few places you guys are kind of simulating things that are measurable or like at least obtainable empirically rather than through simulation.
Yeah, you're right. What's the difference of simulation and actual measuring? Can you go and stand outside for a whole year and measure 1 point? We can simulate 1,000 points in the urban area in less than 4 hours. That's the benefit of it.
So on the second example, or the last example that you showed, it's pretty clear that if the sun's not shining, you're going to be more comfortable. No problem there. On the first example, that analysis or the amount of discomfort hours you would have would definitely depend whether you're in Joburg, where there's sun in winter, versus Cape Town, where there's not that much. Does that get taken into account as well?
Yes, there are lots of parameters that we need to be consider about, and we get lots of them from the weather data station in different cities. Oh, lots of questions. Yeah.
I'm interested to hear about the people behind this. Are you architects with software experience, or are you software guys working with architects?
I've got my master in architecture, and I started to do some programming since 5 years ago. Yeah.
I'm asking this as someone who's actually written simulators. So, do you find that you're using mainly commercial simulators, and you find they're usually very accurate, or do you still need to go occasionally and make measurements and confirm that your calculations are accurate, or is it kind of a very mature field?
The challenges that I did show you guys, it was there were some new challenges in architecture, which we don't have a software, for example, Autodesk version, to use and optimize the Skylight in a cell, Voronoi cell in Johannesburg. So we had to write a code for it. But in many cases, we use radiance, for example, to analyze the daylight, simple cases.
Do you use any processes to manage all this data? Is it reusable between projects? Do you collaborate with other firms?
Can I ask you to repeat your question?
Okay, so all the data you would collect from one project, would it be reusable in another context? And how do you manage all the data that you sort of produce?
Okay. We usually start with the very basic concept of the architect or urban designer, and we do the 3D modeling in Rhino, and we start analyzing the basic concept in terms of outdoor comfort or visual discomfort or different criteria, and we try to improve the design and give the architect some feedback about if you rotate your building, for example, 30 degrees, gonna get less, you're gonna have better daylight or something like that. Then, it's the sense. We can apply the sense to other building as well.
Any more questions? Cool. Thank you very much, Naveed.
Thank you.